by the way. $10 on Amazon.
Cover shipping.
That is. And don't fall for the thing where they want you to sign up for the credit card or for the Amazon Prime, the free trial.
I've already done 3 stuff.
Okay, so we got our up and down forces. What other force would you draw? Friction. And what direction is friction going to be? Going to be to the left, because it says the horizontal force is to the right. So we've got some frictional force. I tend to write F sub F. Sometimes we just see it as like a lowercase f. And then our last force is going to be, let's see, it's pulled, so there could be tension. Tension is either going to be F sub T, the force of tension, or oftentimes I'll just use capital T. Any of those are clear indications that you know what you're talking about. If I drew this correctly, maybe not quite to scale, but it says it moves at a constant velocity. Constant velocity means there is no net force. Obviously there are forces acting on this, but constant velocity gives us the up equals down, left equals right. So the length of these arrows should be approximately the same, based on how I drew it. If it's accelerating to the right, then I would draw my tension force a lot longer than my frictional force, indicating that there's more force to the right than there is to the left. And that's basically what we just did. It says F applied, the applied force. That's multiple ways to represent force. Atwood machines. How many of you love Atwood machine problems? My students tend to have a hate-hate relationship with Atwood. I don't know. It's a really good problem because it involves tension and multiple forces and defining your system, and but they tend to not care for it too much. So draw a free body diagram for both boxes M1 and M2. Assume that no friction acts between box M1 and the tabletop. So for M1, what forces are acting on M1? Gravity. So that's going to be a downward force. And if I've got M1, if the problem tells me M1, I tend to write M1G. I go ahead and include the mass. What else?
Normal force.
Normal force. It's going to be an upward force. Fn. What else? Well, it says there's no friction. So problem 6 friction. You're just testing me, right? See if I would draw it. Yeah, there's going to be a force to the right. And that force is going to be a tension force. And that's it. Looks like I've got an unbalanced force, does it not? So this thing's probably going to accelerate to the right. What about for mass 2?
Downward force. Gravity.
I've got gravity and an upward force. And so this is going to be M2G. And this is going to be the same tension. And that's an important concept. Tension in a rope or a string or a cable is the same throughout. But notice here the tension is to the right, and here the tension is in this direction, but down here the tension is in the opposite direction. So the tension in a rope is the same throughout the entire length of the rope, but at both ends it opposes itself. So that would be the free body diagram. If you release this system from rest, what's it going to do? So M1 is going to slide across the table, M2 is going to drop down. That would be true even if there's no friction, if M1 is a really large mass, 1,000 kilograms, 1,000,000 kilograms. And M2 is a tiny little mass, 1 kilogram. It's still going to accelerate. M2 doesn't have to be bigger than M1, you just have to have an unbalanced force. And it's clear that for M1, if there's no friction, there's no opposing force. So any amount of force to the right, however big or however small, is going to result in an acceleration. And normal, weight, tension, tension, weight. I don't like that they said weight, weight. That implies that weights are equal. They're not. But this is clearly for box 1 and for box 2. 60 kilogram parachutist is falling through the air, 425 newtons of drag force. Act upward on the parachute. How much net force acts on the parachutist? So, if you're doing a dynamics problem, where do you probably want to start? Free body diagram. So let's draw a free body diagram for the parachutist. He's in free fall. What forces are acting on him? Gravity, absolutely. Gravity is going to be a downward force. And you know gravity, I tend to write mg because that's usually what I end up calculating. Any other forces acting on it? Normal, is he in contact with anything? I hope not. Other than the air. But air doesn't provide a normal force. What does the problem tell us?
425 newtons of drag force.
Okay, so if he's accelerating down, as most parachutists do, drag force is going to be in what direction? Up, sure. So my upward force is going to be 425 newtons. So how much net force? How do we find the net force for an object?
Find the sum.
We want to sum the forces. Whenever I draw a free body diagram, I like to identify what I consider the positive direction. And if this parachute is traveling down, I'm going to say down is positive. So when I sum my forces, sum of the forces is the positive forces minus the negative forces. So I take the forces in the positive direction, well that's going to be mg, and I subtract the forces in the negative direction. And the forces in the negative direction, that's my drag force, 425 newtons. So mg, that's his mass, 60 kilograms times g, 10 meters per second squared. And does that make you cringe every time I do that? Minus 425 newtons. 60 times 10, that's easy, right?
600.
600? What's 600 minus 425?
75.
175 newtons. And that's 175 newtons, that's a positive, which means that I have a net force in the positive direction, which is down. If we'd used 9.8 instead of 10, we would have gotten 164. But notice that the other numbers are way different towards the magnitude. If you had added 600 and 425, you'd gotten 1,025 or 1,010. Because you might think, oh, well, it's the sum of all the forces. But you have to take into account the direction of the forces. If there was gravity pulling in this direction, and maybe somebody had a rope and was pulling him down at the same time, then yeah, you would add those two forces because they're both in the same direction. But at a certain point, parachutists reach what's called terminal velocity. They stop accelerating. So if they stop accelerating, they're moving at a constant velocity. There's that term again. Constant velocity means up equals down. Well, if up equals down, what's the net force? 0. So at a certain point, whether you're in free fall or you're under canopy, you do reach a terminal velocity and the net force is 0. Terminal velocity depends on a number of things, surface area and whatnot. That's why the bigger the parachute, the slower the fall. Questions on net force? So take the weight minus 425, you end up with 164 or 175. All right, so question 4 is a continuation. What is the acceleration of the parachutist? Well, now we know something about the net force, and we know the mass, so we're looking for the acceleration. Now this is a straightforward application of Newton's second law. The sum of the forces, 175 newtons, is equal to the mass, 60 kilograms times the acceleration. One step out to the problem at this point. 175 divided by 60, approximately 3. Do I have any of these numbers that are approximately 3? And negative, because it is accelerating down. They use the up, positive, down, negative. So does it, if you were to answer negative 2.73 meters per second down or in the downward direction, either of those would be a clear indication that you need the direction for the acceleration. .96 Newton box slides across the table when a 65 Newton force is applied horizontally and to the right on the box accelerates to the right at 3 meters per second squared. How much kinetic friction force acts on the box? So, where would you start on a problem like this? Free body diagram, always a good choice. If in doubt, start with a free body diagram. Likely that will lead you to a reasonable solution. So you got this box, it's sliding to the right. So we have a force to the right. And that force to the right, they tell me, is 65 newtons. Sometimes if they give me a value for a force, let's go ahead and write the value on my free body diagram. What are they asking me to calculate?
Kinetic friction.
Kinetic friction. So if it's sliding to the right, what direction is my frictional force going to be?
Left.
Yeah, it's going to be to the left. And we've got two other forces acting on this box. What are they? Gravity and normal. So we got gravity in the downward direction, normal in the upward direction. Now, it's not accelerating up or down. The problem would have told us that. So we know the gravity force and the normal force are going to be equal in magnitude, opposite direction. But we're being asked to solve for friction force. What other piece of information does the object give us, or does the
Accelerating
yeah, they give us the acceleration. So we know Newton's second law involves acceleration, certainly. So we can say the sum of the forces is equal to the mass times the acceleration. I know the acceleration is 3 meters per second squared. If it's sliding to the right, make that our positive direction. So what's the sum of forces?
All of the forces combined.
Okay, so combine these forces, the horizontal forces, based on my free body diagram. I've got 65 newtons. I've got 65 newtons. That's a horizontal force. What's my other horizontal force? Friction. So do I add or subtract friction? Subtract, yeah, because it's in the opposite direction. Minus the force of friction is equal to the mass times the acceleration, which is 3 meters per second squared. What am I trying to find? Friction. Well, I've got a number here. I've got a number here. I don't have the mass. Does the problem tell me the mass? Yes? No? What have I not used out of the information that was given? 96 newtons. So 96 newtons, that refers to the weight of the box, right? So if the weight is 96 newtons, that's M times G, right? Well, I want M, so what is G? 9.8 or 10. I'm going to use 10 because I like to divide by 10. So that tells me the mass is 9.6 kilograms. So all of a sudden I've got 65 newtons minus force of friction is equal to 9.6. I'm going to leave my units off because I'm running out of room over here. 9.6 times 3. It's an algebra problem. To isolate the force of friction, I can add it to both sides. And then take 65 newtons, divide that by 9.6 times 3. And I get, let's see. Force of friction of approximately, if you use 9.8, you get 36.2. Or if you use 10, you get 36.2. If you use 9.8, you get 35.6. So a little bit of a wrinkle in that they give you the weight. Some of my students will say, oh, 96, that's the mass. It's like, no, that's the weight. W is equal to mg. It's a pretty easy conversion, pretty easy calculation to go from mass to weight or weight to mass. Some of you might, if you saw this problem, oh, kinetic friction. I know that. That's mu Fn. But the problem didn't give us mu. You can figure out Fn is going to be 96 newtons. But if you think, oh, friction, I have to use force of friction is equal to mu Fn, this problem's not going to help you. There's no mu. It does not exist. But if you draw your free body diagram, oh, well, I need to figure out the frictional force in its entirety, then, well, some combination of frictional force and 65 newtons is going to give me that 3 meters per second squared acceleration. This is another fairly typical type of problem in that you have multiple objects, multiple masses. You've got a 3 kilogram mass and a 5 kilogram mass. They're attached by strings. They sit on a flat table. There's no friction. That's nice. I don't have to worry about a frictional force. An applied force of magnitude F to the right is applied to the 5 kilogram block. So there's some force F being exerted in this direction. What is the tension in the string that connects the two masses? So there's some tension here tension on block A is to the right, tension on block B is to the left. In general, do you think the tension would be less than, equal to, or greater than the force F applied to block B?
It was gonna be like
If you look at just block B, this thing is being accelerated to the right. So look at block B. It's being accelerated to the right. It's got a force F in one direction and a force T in the other direction. Are those going to be equal? If they were equal, then it wouldn't be accelerating. So F related to T is going to be what? Greater than T. So when you're pulling something, you care about, think about the locomotive at the front of a train. It's attached to just one car. But that car is attached to another car, which is attached to another car, which is attached to another car. You know, there might be 120 cars in the train. That locomotive is pulling all of them, all 120 cars. So it cares about not only what it's attached to, but everything behind it. Meanwhile, if you go to the 119th car, how much is it pulling? One car. It only cares about that one car. So the tension in that hitch is going to be a whole lot less than the tension in the coupling between the locomotive and the first one. Same thing holds true with blocks like this connected via strings. If it's accelerating to the right, the tension in each string is going to get progressively less and less the further you go. So we know the force F right here. We're wanting to see how the tension compares to the force in F. Common technique is when you're drawing a free body diagram, you want to define what your system is. From the point of view of this force F, it doesn't really care if it's attached to an 8 kilogram block or a 5 kilogram block plus a 3 kilogram block. It's pulling all 8 kilograms. So if we use the Newton's second law, the sum of the forces is equal to the mass times acceleration. The sum of the forces, notice that tension is entirely contained within the system. I'm only interested in the forces that act across the boundary of the system. So the sum of the forces is simply F. The mass is 8 kilograms. So I can solve for A by dividing both sides by 8 kilograms. So the acceleration is going to be F over 8 kilograms. Both of these blocks have the same acceleration. You know, they're not attached via a bungee cord or anything weird like that. So for this entire system, A is F over M, the applied force over 8 kilograms. Now let's just look at my 3 kilogram mass. What's the net force acting on this 3 kilogram mass? Second. Well, the same as on the first one, except force is not acting on block A, it's just the tension. It has the same acceleration, but for block A, I can say force is equal to MA, so tension is equal to mass times acceleration. So tension is equal to 3 kilograms times my acceleration, which is F over 8 kilograms. So the problem asking to solve for T, how does T relate to F? B, yes, 3/8. Yeah. Another way you could look at it is how much of the mass of the system is the tension accelerating? 3/8 of total mass. If block B and block A, say they were 4 kilograms apiece, then the tension would be exactly half. If you had a 1 kilogram and a 9 kilogram, then it would be just 10% or 1/10. So the amount of tension is proportional to the amount of mass that's being accelerated. Questions on that? Sometimes you'll see a problem like this, where you've got two blocks that are actually next to each other, and it'll ask you for, what's the tension between the blocks. And if you've got, say, a mass of 2 and a mass of 3, depending on the direction of the force applied, it's either going to be 40% or 60% of the if you're pushing in this direction with the force here is going to be 40% because the force here is only pushing 2/5 of the total mass. But if you're pushing in this direction, the force here is going to be 60% because now you're pushing 3/5 of the total mass. We've got some sines and cosines. What do you think that involves? Force operating at an angle. So a push motor of mass M is pushed along a flat frictionless surface. The force of F is applied along the handle of the motor, which is at a 60-degree angle above the horizontal. What is the value of the horizontal acceleration of the motor? Where do you think we need to start? Free body diagram, sure. And so our free body diagram, we've got 3 forces. It would be difficult to push a motor on a frictionless surface. Because if you're trying to push it, your feet are just going to slide out from underneath you. So we'll assume the motor is on a frictionless surface, but you're maybe walking beside it on a track of some sort. So forces acting on the motor, we'll get the obvious ones out of the way. We've got gravity. We've got a normal force. How would you draw the force of the handle? Where would I start my vector, my force vector? Do you ever see an arrow like that on a free body diagram? Yeah. All your forces are going to start on the dot, on the diagram itself. So even though the motor handle is above and you are actually pushing it, from a free body diagram perspective, it would look something like this. And so this becomes my 60-degree angle. The angle between the force and the horizontal, 60 degrees. So we're looking for the horizontal acceleration. It's going to be accelerating in this direction. My gravity and my normal force, I don't really care about. But what do I want to do to this force vector? You have a vector at an angle. This would be the true free body diagram, what you often need to do to solve the problem. Resolve it into its components. So this vector is going to have components to the right, and it's going to have components down. Turns out I don't really care about the downward component. I'm still going to have gravity, still going to have a normal force. But force applied up. Uncle Sam wants you to do what? Sine up. So my vertical force would be F sine theta. So what's my horizontal going to be? F cosine theta. So what's my net force acting on this object, on the lawnmower? Net horizontal force, I've only got one. Right, F cosine theta. So acceleration is F over M, F net, which is going to be F cosine theta over M. Well, theta, they told me, was 60 degrees. So it's really just a matter of breaking that component at an angle into its components. Breaking that force vector at an angle into its components. If you wanted to figure out the, actually, F sine theta is a downward force. Turns out you don't need it, but if you were asked to figure out what's the normal force, you could say up equals down, Fn equals mg plus F sine theta. Normal force is going to be a little bit greater than the actual weight, because if you're pushing down on it with more force, the ground has to push up with more force. All right, we're back to our friend the Atwood machine. Atwood machine has a 10 kilogram mass. This is the same one that we saw earlier, except now they give us the actual masses instead of just M1 and M2. What is the acceleration of the 5 kilogram mass when it's released? So we're looking for the overall acceleration. I don't like how they've drawn the positive directions here. When I do Atwood machines, I say that the positive direction follows the string, follows the direction of motion. So M1 is going to be positive to the right, M2 is going to be positive downward. This is another example of defining your system. Both of these masses are going to accelerate, just like the two that were on the horizontal frictionless surface. So if I define both of these masses as a single system, I can say that the sum of the forces is equal to the mass times the acceleration. Well, what external forces are acting on this system? Gravity. Okay, so we got gravity, M1G. Well, notice tension, the string. It's entirely within the system. So tension is internal to the system, it cancels out. I do have M1G here, and I've got the normal force here. But notice that neither of those